Now I have a lot of electrolytic capacitors, as you can see there. A few more here. Another box there. Others lying around all over the place in this disaster. Now most of these are from IBM mainframes from the 70s and 80s, and IBM did not skimp on quality. They needed to get total reliability, so they didn't skimp on the quality of the parts they used. So I'm very sure that nearly all of these are just fine, even though some of them are getting towards 50 years old. They do need to be reformed, of course, because electrolytics need the oxide layer reformed even if they haven't been used for only a year. Now that's going to take a lot of work to reform and test all those, so I want to make some sort of a automated contraption to do that. But I have a more immediate need to do to reform the electrolytic capacitors in the power supplies of my PDP computers. So automated tester for these things is a long-term project. In the interim I've done this thing, which is a very simple device. It's just basically a switch, a few resistors and a meter. If we look inside, the meter, it's got two ranges selectable by the switch, milliamps or microamps, so 50 milliamps or 50 microamps full scale. There's a switch that's got a capacitor for charging, discharging and slow charging. And the terminal set, not much in there. The circuit for it is this. So a switch with 6 positions. The capacitor under test goes into 2 of the terminals here, power supply in there and an external voltmeter there. So that's those 3 things here. There's the 6 position switch, the 3 resistors that charge fast, charge slow and discharge. When it's charging slow it goes via this meter, a couple of diodes for protection and a switch to bring in this shunt that increases the range to 50 milliamps instead of 50 microamps. So it's very, very simple, and you can do a few things with it. Now, first of all, to reform you would set the, always you should discharge capacitor before you connect it. Then voltage set, which only connects the power supply to the meter, so you can adjust the power supply to get the voltage that you want to charge the capacitor to there, but the capacitor is not connected yet. Then switch it to charge slow, so it'll then start putting the power supply into the capacitor, and you can see it. You can monitor the current here on the meter in the milliamp range. It'll eventually drop down until it gets to a very low current, hopefully, if there's nothing wrong with the capacitor, and then you can switch to microamps and see it drop down further with more accuracy. That's for reforming. You would start off with a low voltage, much less than the rated voltage of the capacitor, and charge it up to that first. Then go to voltage set, change the voltage on the power supply up another increment, say another 10%. I'll start off at 10%, go up another 10% each time, go to charge slow, leave it for quite a while each time until it's drawing in the microamps before voltage set, go to the next 10% increment, charge slow again until you're putting in the maximum voltage and you've got hardly any current even on the microamp range, or when it's stabilised. For testing a existing capacitor that's already been reformed, you just put it on voltage set to set the maximum voltage of the capacitor, switch it over to charge fast, which is a lower resistance, doesn't go through the meter. You just watch on the voltmeter there to see that the capacitor is charged up to the voltage you put on the power supply, and then you can do, say, switch to there, which voltage monitor, which just has the voltmeter sitting across the capacitor, and you can watch the capacitor discharge through the voltmeter, and depending on the impedance of the voltmeter, that might take a while, and so you're essentially seeing if the capacitor can hold a charge. Or you can switch it to disconnected, which makes the capacitor not connected to anything, leave it for say some time, switch back to voltage monitor and see that the capacitor still has most of the voltage you charged it up to on it. If it has, make it disconnected again, wait a while, come back in and see, yep, it's still charged, and when you're finished, discharge the capacitor. Or you could fast charge it and then switch to charge slow, and probably microamps, and see that the current keeps dropping to some final minimum, and decide whether or not that minimum is acceptable. That'll be the leakage on the capacitor, which should be down into the microamps, even for big capacitors. There's the power supply and meter I'll be using, power supply, meter, and good excuse to fire up the Schematic and see a bit of Nixie goodness. I'm just checking the input impedance of the Schematic, 10 megohms, just like any normal multimeter. So he goes in there, and the clip leads for the capacitor under test. No, that's wrong, idiot. Meter goes there, cut goes here. Volts right down. Make sure you get these wires around the right way. Double check everything that's on the plus. There. Double check. Plus, 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 all good. Okay, so I want to charge this up. It only goes to 6 volts, so I'll do the first step at 1 volt. So I'm looking at the meter, turn it to voltage set, wind this up and get 1 volt on the meter. And it doesn't matter if I go high because it's not connected to capacitor yet, so there we go, 1.05 volts. So now we'll charge slowly, so the power supply is then connected to the capacitor via a large resistor, 470 ohms, this guy, and via the meter. There, and we'll switch it to milliamps. Put it there so we can see better. And we can also see the voltage that the capacitor charges up to. So initially, when I connect it across, this will be a dead short, so it'll load down that resistor. The voltage across the capacitor will drop, but gradually rise as the current charges it. So we'll see all that. Charge slow. Voltage drops. Very low current because we're only pushing a volt. So we can almost switch to microamps. No, it's beyond that. Got to wait for it to. We want to get almost to 0 because remember that's 1,000 volt, 1,000 times change in current. So almost nothing here is still off the scale in microamps. Right, I ran that for a while with this capacitor and I had it charged to 1 volt, and I switched it to charging up to 2 volts, and when I came back after a while it had dropped down to below a volt, and you know, this capacitor has failed. It's turned into a low resistance. There's no capacitance in it at all, and this little multifunction tester confirms it. Takes a while to test big capacitors, but it's turned into 0.07 ohms. And this, so then I went to this one, which is 66,000 microfarads, 30 volts, and it reformed and charges up. It works okay, but it's got a fairly high leakage. So if I just switch that up, voltage set, take that to 30 volts, 30.01, charge. See, the meter goes off scale when we're charging this much voltage difference, so it charges fast, so it builds up quickly to 30 volts. And now it's close, so I'll switch to charge slow, and even after hours that will still be running at about 1 milliamp. So if I go to, if I switch to microamps, it's off the scale, and it never really gets less than about 1 milliamp. And the problem with this testing arrangement is that there's 3 different resistors there. We've got, in fast charge we've got 47 ohms, in slow charge via the meter in milliamps it's about 470 ohms, and in microamps it's about 3,300 ohms because you've got the resistance of the meter added in, or you don't have the shunt across it, so it comes out to 3,300. And those 3 resistances form a voltage divider with the resistance, the leakage resistance of the capacitor. It may be that the voltage divider formed with the 3,300 ohms and the leakage resistance of this is so much lower than the voltage we're trying to put into it from the power supply, that the leakage current is always going to be way off scale, and that's the case with this guy. So we have to go to milliamps, and there's about 1 milliamp of leakage, which is, I think, probably still within specs, although the formulas that the different manufacturers give make it a bit confusing, and it depends on whether you're talking about acceptance leakage current, which is after you've just let it run for 5 minutes, or whether you're talking about operating leakage current, which is when it's had an hour or so to reform. So it is a bit of a judgment call, and although this is by no means as good as I've seen, it's still a capacitor. It still works, but this guy's cactus. But and I recorded all that, but I didn't like the way I was narrating it, so I've thrown it all away. I might try a couple more. We've got 100,000 microfarads, 20 volts, and 650,000, more than half a farad, but only at 6.3 volts. So we'll do him next. Alright, now this one, voltage set to 1.04 volts, so we'll go to milliamps, charge slow, small current there. Alright, it's been about 40 minutes and we're at 1 volt. I'll switch to the 5 volt range. And next increment is, let's go to 2 volts. So voltage set. Alright, now we'll charge to that. Charge slow, and it's building up from 1 volt. Oh, about another 20 minutes, not quite at 2 volts. Let's look at the voltage set, see what it should be. Yeah, it's got a bit to go yet. If we look at the current on microamps, it's 25 microamps, and is it falling? Well, it's not increasing. That's a good sign. No, the voltage is dropping. Alright, I'll leave it on milliamps where there's a lower resistance to the capacitor. As I say, it's all a bit of a judgment call, but this capacitor's looking okay so far, but let's see what happens when we get up to its rated voltage of 6 volts. I've had quite a break, probably near an hour. Microamps, it's right down even on microamps. Let's take it up to, let's give it a big jump, let's go to 4 volts. So voltage set, okay, back to milliamps, charge slow. So we're climbing from 2 volts to 4 volts. I read somewhere that reforming current should be no more than 5 milliamps, so maybe that's a way to do this much faster, is to just keep increasing the voltage but keeping the current going into the capacitor to no more than 5 milliamps. That might be a quick way of reforming things, more for an automated contraption rather than doing this manually, but something to think about. Alright, time to move up to the next setting, the last one, 6 volts. Change ranges. Okay, back onto charge slow in milliamps, going from 3.9 up to 6. Right, 5.89 volts out of a possible 5.95. Looks to be as close as it's going to get. If we look at that in microamps, just under 20. I'll say that capacitor's okay. Let's see if it can hold a charge now. So back to milliamps for safety, and we'll go to voltage monitor. There's the 5.89 sitting on there. We'll leave it disconnected for a while, so the capacitor's just discharging through its own leakage resistance. Alright, it's been about an hour and 20 minutes. Let's see if it's still got 5.89 volts on it. We go to voltage monitor from disconnected. 5.51. I think that's pretty good. I'd say that's a good capacitor. So now we'll discharge it. And I've got one other from there that I want to try. 100,000 mic, 20 volts. So we'll charge him up to 5 volts first, and I'll take off this bleeder resistor and stuff. Okay, now this guy, set the voltage to 5 volts and slow charge. 10 milliamps. We'll let it run at 5 volts for a while. It's only been about 10 minutes and yeah, already pretty close to 5 volts, so let's switch it up to the next increment. Voltage set. We're going to 20, let's do it in 5 volt lumps. So we'll take it up to 10 volts now. Okay, charge. again near 10 milliamps, but drops as the thing charges. It's been about 20 minutes and 9.84 volts out of a possible 9.98, so it's not quite getting there. If we look at microamps, it's fairly high and rising. Now that might come good if I leave it on for longer, so we'll do that. I probably should have been writing all these times down, but oh well. It's been another half an hour-ish and the voltage has gone up a little bit. And if we go to microamps now, it was up around 50 I think and climbing, but now it's 25, still climbing slightly, so it is getting better. I'll give it another while and see how it comes. Maybe another half hour I suppose it's been, and voltage crept up a touch. Current has dropped, so it's improving. Still rising slightly in the microamp range, but getting better all the time. And it'll reach some limit where it won't get any better and you have to make a judgment call. Is the thing good enough? I'd say that's a pretty good capacitor anyway. The specs in the data sheets vary all over the place. They're usually given as the capacitance multiplied by the voltage to some power less than 1. So to raise to the power 0.7, 0.85 or 0.5, which is square root, and then multiplied by some factor, and that's how many microamps you should get. And I'd say this is well within the specs. Most manufacturers, you have to look up each one and they're all different. Time to go up to 15 volts I think. So voltage set 15 and charge milliamps, again up about 10 milliamps and it'll drop down. And it's probably been another hour. Let's see how many microamps we've got. About 30, climbing, so either this is as good as it gets or it can improve some more. I'll just put it back to milliamps and we'll let it run at 15 volts for a bit longer. So it's been quite a while, 4 or 5 hours. We've got right up to 15 volts out of 15.04, so it's very highly charged. In microamps it should be pretty low current. 12, slowly climbing back to milliamps, and let's go the last step up to 20 volts. Charging again about 10 milliamps. Alright, quite a few hours trying to get up to 20 volts. We're up to 19.91. Let's see what the power supply's got. 19.99, so very close. Current on microamp range 23 and climbing ever so slightly, so that's as far as we can go with that one. But yeah, I classify that capacitor as good. I've seen lower leakage, but that's okay. Let's see how well it holds the charge. So we're at voltage on it 1989. We'll run disconnected for a while and come back and see how much it's dropped from 1989. Right, it's been almost 2 hours sitting there disconnected. Before it was disconnected it had 19.89 volts on it, so let's go to voltage monitor and see what's there now. 16.07 after 2 hours. Yeah, that's alright I reckon. Not brilliant, but certainly not a dud. I'll count that as passed. So here's my 4 capacitors that I've reformed and tested the leakage with this little gizmo. This one turned out to be a complete fail, turned into a resistor. This one, it works, it's a capacitor, holds charge, but compared to these guys it's got a fairly high leakage current of 1 milliamp at 30 volts. These guys are down in the microamps, so a bit sus and a fail. So maybe my earlier confidence in IBM's choice of capacitor manufacturers was a bit misplaced, but I'm still hopeful that most of that box I've got out in the shed are like these guys. Of course, you've got to remember, or I've got to remember, these things, these electrolytic capacitors here, prior to a few days ago, had not seen an electron since disco was a thing. They're 30, 40, 50 years old, some of them. Yeah, there's going to be some deterioration, but I'm hopeful that most of them are perfectly usable. And to buy these things today, you're looking at new, some of these things would cost between $75 and $150. So if they work, that would be great. Now, I just want to also test each of these with this guy just to see what capacitance he reads and what equivalent series resistance, ESR, that it finds, because this thing doesn't test any of that. Well, it can crudely test capacitance by charging it to a voltage, discharging it and timing how long it takes to discharge through the 100 ohm resistor that's in here, and from that you can work out the capacitance, but it's clumsy. Anyway, before using this guy, if I was just to put it on there now, it would show them, some of them, as not a capacitor but as a cell, because of dielectric absorption, where charge is stored inside the insulating layer inside the capacitor, and it comes out over a period after any discharge circuit has been removed. It gradually builds up charge and will look to this thing like a battery or a cell rather than a capacitor. So before using this, I have to re-discharge each of these to 0 volts. Now I'll just throw this one onto, now that it's been reformed, throw it onto here and see what it says. Should be 66,000 microfarads. 83,930 microfarads. ESR 0.34. I don't know how accurate that is at the capacitors like this, but yeah, can be plus 150%. So 83,000 was it? Is certainly within range. So that one looks okay. And this one, now, got to make sure that there's no charge come out of the insulation inside. Yeah. Now this is 650,000 plus 50 minus 10%, so it could show up as a farad actually. There we go, 127 millifarad. What's that? No, millivolts. It's still showing up as a battery. Got to make sure that that is discharged. Try again. Now it looks like a bloody resistor. No, I just don't think this thing's up to testing capacitors that big. Let's try this last one. 100,000 microfarads. Make sure it's discharged. Capacitor, 109 millifarads. Very close to the 100,000. ESR 0.34 again. So that one looks good. I think this one, I'm sure, is good. We tested okay for holding a charge. I just don't think this thing can deal with a capacitor that big. So there it is, my simple little capacitor reformer tester. It's just, as I say, a switch and a bunch of resistors and a meter. It mostly saves having to switch between the charging and the voltage setting, but these other positions are also of some use, so they're included. Yeah, I found it helpful, useful. I've already used it to check out these capacitors from my PDP computers, and they're pretty much all right. There's one or two that are slightly sus, and yeah, I'm pretty happy with this thing. So I hope you found that interesting and enjoyable, and I'll catch you later.